Okay, this video is all about gas chromatography and mass spectrometry. So the first thing you need to know is why we would use gas chromatography instead of normal chromatography. It's quite simple really. Normal chromatography needs things to be coloured. You can only separate coloured substances, for example pens, dyes, things like that, with normal chromatography. With gas chromatography you can separate pretty much any compound that you have. So gas chromatography is really, really useful. We're looking still at separating substances. That's the whole point. It's separating a mixture of different compounds. So we're not separating compounds, we're not separating things that are bonded together, but we're separating a mixture of different compounds. So a mixture of compounds. So when might you need to use that? Well, it's used quite regularly in drugs testing for sports events, so for the Olympics and things like that. So drugs testing, either using urine or blood. Okay. So gas chromatography comes in, you take a small sample of urine and you'd separate it in this machine here. So this is the gas chromatography machine. It's really important to know that you'd use a machine because it's fast, because it is accurate, and because it's sensitive. So three really important points there. Machines are fast, they're accurate, and they're sensitive. Okay? It's an instrumental method. So you might hear it referred to as an instrumental method. And these are fast, accurate and sensitive. That means you only need a small amount of your sample. So you'd only need a small amount of urine or blood in order to be able to separate it out and see what different compounds you've got in there. So let's have a bit of a closer look at our machine. So it starts off here with our carrier gas. Now it's really important that that carrier gas is inert. What that means is it won't react with anything. That's really important because when you put in your sample, the last thing you want is for chemical reactions to happen. If chemical reactions happen, you'll end up with totally different compounds. And that won't tell you what compounds there were there originally. So an inert gas won't react. The gas is pushed in and the flow can be controlled by a flow controller here. And it's pushed into this column. Now the column here is a solid. So we've got already our mobile phase, which is the gas, and we've got our solid phase here, which is our solid column. Now the solid column has gaps in it which will allow the gas to flow through. So we've got solid, gaps for our sample to flow through. So in comes the gas, and here is where the sample is put in. So the sample will usually be vaporised to turn it into a gas, and it will be added to this carrier gas, and it's the carrier gas that carries the sample all the way through the column. Now don't forget, in our sample we've got lots and lots of different sized molecules because we've got lots of different compounds, lots of atoms. Urine and blood is full of lots and lots of different compounds, all different sizes. When they get into this solid column, they get sort of squeezed through. So they're not all going to travel through at the same time. Some of them are going to get held up, some of them will actually interact with the walls of the column, and that will slow them down. So as they go through, they start off here all together in your sample, and then as they go through, they get carried at different rates through the column. Eventually, when they come out of the column, they'll come out and you'll get this thing here. This is called a chromatograph. It's the reading that you get out at the end of your gas chromatography. So it's called a chromatograph. So let's have a bit of a closer look at that now. So this is my chromatograph here. Okay, it looks like a normal graph. We've got these two axes. Along the bottom is time. Okay, so that is the amount of time that the sample has spent inside the column. So spent in column. Okay, like I said, different compounds will spend a different amount of time in the column. Then you've got this axis here, going upwards. That is the strength of the response. Okay, and that tells you how many of that particular compound you had in your mixture. So if you had lots and lots of a compound, you get a big peak like this one in the middle. If you had not so many molecules of a compound, you get little peaks like this. Okay, so a couple of things that you need to know about reading a chromatograph. First of all, you need to count the number of peaks. Peak 1, peak 2, and peak 3. That tells us how many molecules you have in your mixture. So we have 1, 2, 3 different compounds in our mixture. Okay, then once you know how many different compounds you've got, you also can tell how long each of those compounds spent in the tube. It's called the retention time. So by looking down here, we can see the points at which each of these came out of the tube. So whatever compound 1 is, came out first. It spent the least amount of time in the tube, so it would have the smallest retention time. Compound 2 has a medium retention time, and compound 3 has the longest retention time. So that's what you get when you look at the readout from your gas chromatography machine. However, you can't work out just from that what compounds you have there. And obviously if you're testing for something like a drug or something in the urine or the blood, you need to know what compounds you have, otherwise the test is fairly useless. So that's when a gas chromatography machine will be attached to a mass spectrometer. And when they're attached together, they are shortened to GCMS, or sometimes GCMS linked. Okay, and that tells you you've got gas chromatography and mass spectrometry working together. From that, you get a slightly different readout, so a slightly different type of graph. So you get a graph that looks a little bit like this. Again, we've got two axes, but this time, up the side, we have relative abundance. And along the bottom, we have MZ. You don't need to worry about what that means, okay? This is the readout you get if you pass each compound through a mass spectrometer. And a mass spectrometer's job is to separate compounds and tell you what you have in there, the molecular mass of what you have in there. So you can find out the molecular mass of each of our 3 different compounds by passing each one through a mass spectrometer. So let's imagine that we pass this first compound through here. We get a reading that looks like this, and the only thing we're interested in is this final column, this final bar on our graph, the one to the very, very, very far right. This is the one that will tell us what our overall mass of our compound is, or our relative formula mass. So the rest of the bars we don't need to worry about, we just worry about this one. So, for example, imagine that came out at 18 here. A question might give you this and ask you to work out what compound has come out. So, obviously, lots of compounds are going to have a relative formula mass of 18. But the question might give you several options. So, for example, it might say sodium chloride, water, or magnesium oxide. So it will give you 3 options. And you have to work out which one this final bar represents. So you get your periodic table and you work out the relative mass of each of these. So the only one that adds up to 18 is water, because we have 2 hydrogens, which weigh 1 each, and an oxygen, which is 16. So it must be water. So that's all you really need to know about gas chromatography and mass spectrometry. Don't forget the different parts here. We have an inert gas that goes through, the sample gets vaporised and injected in, and that inert gas is there to carry the sample through. So this is not our sample down here, our sample comes in up here. It joins that carrier gas, and the carrier gas carries it through the solid columns. We've got our 2 phases, our mobile phase and our stationary phase. It then comes out at the end and you get your chromatograph, from which you can tell how many different compounds you've got, by how many peaks there are, and how long each compound spent in that column. Then you attach your mass spectrometer, and each compound will give you a relative formula mass. So you get a reading for each of these different compounds, and from that you can select which compound it is based on the relative formula mass.